are talking about systems of equations. We've talked about writing the equations of lines and slopes. We've talked about the standard form of equations and the slope-intercept form, and then how to get to those forms. And today we're talking about solving systems of equations. And what a system of equation is two or more linear equations on the same graph, right? Two or more linear equations. And I'll post these notes in your classrooms on the same graph. There are, I should put same graph, same. There's three types. They're all listed there. You've got one solution, no solution, and an infinite number of solutions. When you have one solution, say I have the graph of an equation that looks like this, and I have the graph of an equation that looks like this. Where these two intersect is our solution. That point of intersection. And it doesn't matter if I have like three different lines graphed on here, where all three of them would intersect, would be the solution for that system. That means that that solution, that x and y coordinate, is true for both equations, right? It's going to be a true point for both equations. Or if I have three lines that intersect at the same point, it would be true for all of them. So if one solution is the graph of two lines that intersect, what would you assume no solution would be? Yeah, they don't intersect. What kind of lines don't intersect? What kind of lines never touch each other? Parallel, very good. So when we have no solution, we're talking about the graph of parallel lines. Let's see if I can make these look even remotely parallel. And that's pretty good. It's not too bad. Infinite solutions are when the equations of the lines are multiples of each other. So if I have an equation that graphs like this, and I have another equation that like that. And I have another one that graphs right on top of it. They say they have infinite solutions. Anytime you come to one that has infinite solutions, if you put it in the equations of those lines into that y equals mx plus b form, those lines would wind up being identical, right? They would have identical equations. So you can always kind of tell. No solution, when you have them in that y equals mx plus b form, they're going to have the same slope, right? Because all parallel lines have exactly the same slope. And all things that have exactly the same slope are parallel lines. So below, we're just talking today about solving by graphing. Is it the most effective way to solve? If you have a computer, absolutely. And you guys are going to be doing yours on Delta Math, so you do have a computer to use. It makes it a whole lot easier. But when you're either drawing the graph or trying to be perfect on this, it's not always the most accurate thing, right? It requires that you draw straight lines for one, which I'm also really terrible at. But you get the general idea. After this, we'll start talking about how to do it algebraically, but that's for another day. Notice that these first lines in number 1 are in that slope-intercept form. They're in that y equals mx plus b form that actually flicked on there. So this y equals mx plus b form is awesome in that it allows us to graph it really easy. We don't have to do anything to these equations to be able to graph them, because we know that right here we have a y-intercept at -6. So we have a point right there at -6. And I have a slope of -5/3, right? So I can always find my next point. If you remember, when my m equals something negative, I can either make the top negative or the bottom negative, just not both. So I could go down 5 places, which I don't really have room for. So I'm going to go up 5. So I'm going to go positive 5. 1, 2, 3, 4, 5. And I'm going to go negative 1, 2, 3. And there's going to be my next point. What's cool about that is you can always count out the next point too, but all we really care about is connecting those rods. So when I go to do the graph of the next line, I know here I have a point at 5 on the y-axis, right? Because that's my y-intercept. And I have a slope of 1/6. So I can go up 1, positive 6, or I can go down 1, -6. And the reason I'm picking that one is because down 1, -6 is because this line is actually supposed to be going right through this point. And so that is where they are going to intersect. Right? And I'm able to find this solution. If I were to draw this straight, I would have found this point right here that they both intersect, which is at -6. That is my one solution. Does that make a little bit of sense? So if we look at sheets, if we look at number 2, we have y equals 5. Y equals 5 is literally at 5. We have a graph that goes all the way this way and all the way that way. That's all y equals 5 is. The other part, though, is y equals 2x plus 7, which means that I'm going to have a point at 7 on the y-axis, and my slope is going to be 2. So I would go down to -1, or I could go up to +1, but I knew where my points were going to cross. And right here at -1, 5, I have a solution. -1, 5. So that's all we're looking for, is that point of intersection. They aren't all going to be in slope-intercept form. Sometimes we are going to have to change the form of the equation. If we look at number 3, I have 6x plus 5y equals -45. I need to put that in slope-intercept form. So 6x minus 5y equals -45. I need to solve it for y. I'm going to start by subtracting 6x from both sides. And I get minus 5y equals -6x minus 45. And then I have to divide this -5 out of each piece, right? So this becomes y equals 6/5, because negative over negative is a positive. 45 divided by 5 is, oops, sorry, plus So when we go to graph this line, now we're in slope-intercept form. We go, okay, here's a point at 9. My slope is 6/5, so I can go negative, negative. I can go negative 1, 2, 3, 4, 5, 6. 1, 2, 3, 5. And I connect those dots of the graph. If I notice 2x plus 2y equals negative 4, also not in slope-intercept form, but we can put it there. We can go, okay, well, we've got 2x plus 2y. I'm going to try and fit it over here. 2x plus 2y equals negative. We start by subtracting 2x from both sides. And I get 2y equals negative 2x minus 4. So the only thing I have to do now is divide everything by 2. And I get y equals minus x minus 2. So here we know, negative 2, we have a point. Our slope is negative. And because we don't have a number there, doesn't mean that our slope doesn't have a number. It's negative, m equals negative 1. Right? So I could write that as negative 1 over 1, and I could either go up 1 and negative 1, or I could go down 1 and positive 1. I could do this forever because 1s, they're kind of handy, and that they always follow this little pattern right here. And our solution is going to be at this point, negative 5, where they intersect. We're only going to do 2 more because they have different types of solution sets. So we're going to switch over here to number 4. Now, one of these equations is already written in slope-intercept form, but if we look at the first one, it is not. So we've got to take this 3x plus 6y equals negative 12 and get it into our slope-intercept form. So I'm going to start by subtracting 3x from both sides. I'm going to get 6y equals minus 3x minus 12. The only thing that's left being done to this y is it's being multiplied by 6. So I'm going to divide by 6, divide by 6, divide by 6. And I get y equals, well, 3 over 6 is negative 1 half x. Negative 12 over 6 is negative 2. And if you notice, the slope here is negative 1 half, and the slope here is negative 1 half. You see that? That means that these are going to be parallel lines. We can graph them. I can have my point at negative 2, and I go up 1 over 2, up 1 over 2. I could do this for freaking ever, right? I have this, or I could go down 1 over 2, down 1 over 2. I can graph these forever and ever and ever. And if I look at the other one, I have a point at negative 5. Do a different color. Here I have a point at negative 5, but my slope is the same, right? I can go up 1 over 2, up 1 over 2, or I could go down 1 over 2, down 1 over 2. But these lines are never going to get any closer together. And we know this before we even graph it because they have the same slope. If their slopes are equal, and that means the signs have to be equal. It can't be 1 half and negative 1 half. They both have to be negative 1 half. We know that these lines are never going to intersect. So in this case, we'd graph it, but we'd say there's no solution, right? Let's quickly look at number 6. Number 6, if we look at that first equation, minus y equals minus x minus 6, This is almost in slope-intercept form, except for we have a negative y. So I'm just going to divide everything by negative 1. And all that really does is change the sign of everything. So this becomes y equals x plus 6. And when I go to graph that, it says, okay, here at 6, I have a point. I don't have anything in front of x, so my x is just 1 over 1. So if I go up 1, I go over. If I go up 1, I go over. If I were to go down 1, I go over negative, negative. Get got this line that's going to go forever and ever and ever. If I can draw it straight. Right? The next line, I've got this 3x plus 18 equals 3y. I'm going to rewrite this. And the way I'm going to rewrite it is I'm going to write it as 3y equals 3x plus 18. Same thing, right? I just put the 3y on the other side. They mean the exact same thing. But this way, all I have to do to get it into the right form is divide everything by 3. I get y equals x plus 18 divided by 3 is 6. And looky here, that's the same equation. So it is going to graph right on top of the other line. And we are going to have infinite solutions. Does that make some sense? Before I let you go, I'm going to do one more thing. I'm going to go over to Delta Math just to make sure that you know how to graph them in Delta Math. So I like these because they're already in slope-intercept form. So when you go to graph problems like this and then you want to put in your solution, so we go, okay, well, our first point is going to be that negative intercept of negative 1, which is where I'm going to start. And my slope is 5, 6. So I'm going to go up 1, 2, 3, 4, 5, and over to the negative 6. So I've got my first line graph. So I'm going to go to my second one, and I know my y-intercept is at 6. And my slope is 1/3, but I can go down 1 over 3 this way, right? That's still legit. Or I could have gone up 1 and over 3 the other way. So my common point right here is where they meet. And if you notice, that's at x equals negative 6. You're going to want to put in parentheses, negative 6, comma, where does it meet? At 4 in parentheses when you put in your solution. You just want that point, but you want to make sure you put the parentheses and the comma in the next point in so that it's entered as a proper solution. And you'll see that as well. So I just wanted to make sure you knew how to actually graph these into Delta Math. You can graph both equations, one right after the other, just by having 2 points. And it'll do the rest of the graph all by itself. Your level 2 problems, all of the level 1 problems, which is what you mostly have, are already going to be written in the slope-intercept form. The other part that you have is going to be level 2 problems, and you are going to have to put those in slope-intercept form just to graph them. There's only 3 of those. There's like 7 of the others, but only 3 of the ones where you have to actually manipulate them to get them in the form to graph. Okay? That is all I have for you. I'm going to stop this video